Hi ladies and gentlemen, this is Ms. Skokin. We're here to look at section 1-2, measuring and constructing segments. Our objectives are use the length and the midpoint of a segment and construct midpoints and congruent segments. We've got a lot of vocabulary: coordinate, distance, length, congruent segments, construction, between, midpoint, bisect, and segment bisector. We're going to start with our warm-up, and I'm going to have you pause the video, work on these questions, and turn the video back on when you're ready to check your answers. See you back in a minute. Numbers 1 and 2 were integer questions, and you probably remember that from your middle school math, so hopefully you didn't have any trouble with those. Number 3 is an absolute value question where we're just evaluating the distance away from 0 of the number inside the absolute value bars. Numbers 4 and 5, we needed to solve the equation for the unknown variable x, and again, those were fairly straightforward. You could have done them in more steps than I'm showing here, but if you are not able to get the correct answers, put a star next to the question number so that we can discuss it in class. And in number 6, it says how many real numbers are there between 1/2 and 3/4? And actually, I drew it on a number line, but there are an infinite number of numbers between those two values on the number line. All right, let's take a look at the ruler postulate. The points on a line can be put into one-to-one correspondence with the real numbers. And what that actually means is if we have a segment that goes from 2 to 4, we can consider what the distance is, or the length of that, by finding the difference. So we can say it's going to be the absolute value of 4 minus 2, which is 2. We could also look at it as the absolute value of 2 minus 4, which is still 2. So the distance of that segment, or the length of that segment, the distance between those 2 points, is 2 no matter how you slice it. And the distance between any 2 points is the absolute value of the difference in the coordinates, as I just showed you. The distance between any 2 points is also called the length of the segment between those points. And the notation that we use to show the length of a segment is going to be the 2 points next to each other, but with no bar over them, just as we have here. So we're going to continue to see more examples of the correct notation for segments, for lines, for rays, and then for the distance between 2 points. And pay close attention to the differences in the notation, because it's not hard, but it is something new for you. In example 1, we're using the ruler postulate to find the length of a segment. So to start with, in question A, we want to find the length of segment BC. So BC goes from here to here. And the way that we're going to do that, and I know we could count jumps, but the way that I want you to think of it is this is going to be the absolute value of the difference between the coordinates of the points. So 1 minus 3, you could also do 3 minus 1. This is the absolute value of -2, which we know is equal to 2. So the distance between those 2 points is 2. When it comes to question B, we want to find the length of segment AC. So from coordinate A to the coordinate of point C. This time, we're going to show this as, again, the absolute value of 3 minus -2, or we could do it in the reverse order, -2 minus 3. That we know is equal to the absolute value of 5, which is equal to 5. So the distance between points A and C, or the length of segment AC, is 5 units long. We have a new vocabulary word, congruent. Congruent basically just means that 2 things are the same size. So when we're talking about congruent segments, they are segments that have the same length. And we have a few different ways of indicating segments are equal in length, but we're going to be using tick marks very frequently. So imagine that you can see we have segment PQ and segment RS. They each have 1 tick mark indicating they are the same length. Imagine that as part of this diagram, I have a few more segments, such as segments AB and CD. Now, I already have a pair of segments that have one tick mark each. So because I have these other segments that are also congruent to each other, I'm going to give those 2 tick marks each to indicate their relationship. So this could go on with 3 tick marks, 4 tick marks, etc. And imagine that I had another segment that wasn't the same size as any of these. Well, I could draw that in and it would get no tick marks. We'll call this one XY. No tick marks because it's not the same size as any of these other segments. So we just learned that the word congruent means the 2 things that are the same size. And we use a special symbol for congruence, which is, it looks like an equal sign with a little tilde over the top of it. And you can see in the green, segment PQ is congruent to segment RS. That's how we would read the statement right here. That's how we would read that statement. Now, if we're talking about the segment itself, we would say and they're the same size, the segments are congruent. But if we're talking about the length of the segment, as we see in the line above, the distance PQ, or the length between points P and Q, is equal to the distance between points R and S, that's different. So when we're talking about lengths, notice that there is no bar on top of the point pair. When we're talking about the segment, there is a bar over. So are we talking about the length or are we talking about the segment itself? If we're talking about the segment itself, it can be congruent to another segment, but lengths can be equal. You'll get more practice with this, so I don't want you to worry about it too much right now, but we will be seeing this more and more and more. And I do want you to have an understanding of the notation and the vocabulary. Let's take a look now at the segment addition postulate. In the segment addition postulate, it says if there's a point B between points A and C, then the distance from A to B plus the distance from B to C is equal to the distance from A to C. This seems very straightforward, but it's going to give us some power. It's going to allow us to practice our algebra skills and also use our new geometry skills. So let's take a look at example 3. Example 3 says that point G is between points F and H. So let's just draw what that looks like. And it also says that the distance from F to G is 6, and the distance from F to H is 11. And the question goes on to ask us to find the length GH. And of course it says hint, sketch first. We're always going to do sketches. We're going to have lots and lots and lots of practice drawing this year. So anyhow, we want to set this up using the segment addition postulate. I know that you can do this in your head, but I want you to start using really good geometry habits, which means we're going to set it up using the segment addition postulate first, exactly as it reads in the segment addition postulate that we see on the screen. So we'll say that the distance FG plus the distance GH is equal to the total distance of FH. Okay, now let's plug in the values. So at this point, you can see how simple it is to solve. We are going to subtract 6 from both sides, and we end up with GH is equal to 5. So again, I know that you could have done this in your head, but remember what we're trying to do is learn the good geometry habits, which means we start out with our theorem or postulate, and then we plug in and solve to get our final answer. In part B, we see that point M is between points N and O, and we've got algebraic expressions for the length of the segment NO, the length of the segment NM, and the length of the segment MO. So once again, we're going to set it up using our segment addition postulate. We start out with our geometric notation. So the distance from N to M plus the distance from M to O is going to be equal to the distance from N to O. And then we substitute in. So the length from N to M is 17. The distance from M to O is 3x minus 5. And the whole distance from N to O is 5x plus 2. Go ahead and pause the video so that you can solve for x, and I'll see you back in a minute. Okay, so we're able to solve and get x is equal to 5. And remember, our question was actually asking us to find the distance from N to O. So N to O is the expression 5x plus 2. So we're going to show that, and then we're going to substitute in 5 times 5 plus 2, and we end up with a total distance from N to O of 27. This is the segment addition postulate. We've got another new vocabulary word, midpoint. And if we say that the midpoint that we'll call point M of segment AB, it's defined as the point that's halfway between points A and B. So that means if you can picture our segment from A to B, and we go halfway there, we've got point M. Now, another way to say this is that point M bisects the segment between points A and B, and bisect means it exactly cuts in half. So with our segment AB and midpoint M, we could say that the segment from A to M is congruent to the segment from M to B. They're the same size because point M bisected segment AB. All right, let's take a look at example 4 now. The map shows a route for a race. You are at point X, which is 6,000 feet away from the first checkpoint C. So this is 6,000 feet to point C. The second checkpoint D is located at the midpoint between C and the end of the race Y. That means that these two segments are congruent, or the same size. The total race is 3 miles long, and that would be from point X to point Y. How far apart are the two checkpoints? So one thing we notice right away is that we've got mixed units. We've got 6,000 feet from point X to point C, but we've got 3 miles from point X to point Y. So what we're going to do is we're going to convert our 3 miles into feet. There are 5,280 feet in 1 mile. So if we multiply our 3 miles by this conversion factor, our miles cancel with miles. We multiply 3 to the 5,280, and we end up with the total number of feet, which is 15,840 feet. Now what we're going to do is we're going to set it up just like we have in the segment addition postulate, but I want to substitute in for the two segments that I know are the same size, and we can call them anything. I'm just going to call this distance G, and that means that this distance is also called G. So when we set it up, we're going to say the segment from X to C plus the segment from C to D plus the segment from D to Y is equal to the whole thing, which goes from X to Y. And now we're going to substitute in the specific values that we know. So from X to C, we have 6,000. From C to D, we have G. From D to Y, we have G. And then from X to Y, we have our 15,840 feet. And we can easily solve this. We're going to have 2G here, 6,000 plus, and 15,840. To solve for G, we subtract 6,000 from both sides, and we end up with 2G is equal to 9,840. We divide both sides by 2, and we end up with G is equal to 4,290 feet. Let's go back and make sure that we have answered the correct question, and it says, how far apart are the two checkpoints? That means we're looking for the distance from point C to point D, and we have found that because that's what we called G. So the distance between the two checkpoints, or the length of segment CD, is 4,290 feet. So we learned a few new things in this example: midpoint, bisects, and setting up a diagram using the segment addition postulate. Now, let's talk about a segment bisector. A segment bisector is any ray, segment, or line that intersects a segment at its midpoint. It divides a segment into two equal parts at its midpoint. Here's an example. Let's say that we have segment AB, and we have a line that we'll call line L that intersects segment AB at its midpoint. So that means line L is a segment bisector of segment AB. And it also means that we've got a pair of congruent segments, because when we cut something exactly in half, those two halves are exactly equal. Let's take a look now at example number 5. This is our last example until we get to our practice problems. Example number 5 reads, using midpoints to find lengths. D is the midpoint of segment EF, and then we have an expression for the length between points E and D and between points D and F. And then we're asked to find the distance of segment ED, or the length of segment ED, the distance between points D and F, and the distance between points E and F, and it says hint, sketch. So let's start with a sketch. We'll start out with segment EF and the midpoint D, exactly at the halfway point. And then we'll put in our expression. So from E to D, we've got 4x plus 6. From D to F, we've got 7x minus 9. Now, we know because the point D is halfway, or the midpoint, of segment EF, we know that we've got two congruent halves here. So we're going to set it up as an equation with length ED equal to length DF. So now that we've got that set up, we can substitute in. So for ED, we're going to substitute in 4x plus 6, and we're going to set that equal to the length of DF, which is 7x minus 9. And at this point, we can just solve like we always do. So we'll say 7x minus 4x is going to be equal to 9 plus 6. So 15 is equal to 3x, and that means x is equal to 5. Okay, not what we were looking for, because just a reminder, we want to find the length ED, the length DF, and the length EF. So that means that we need to plug in. So we're going to start by plugging into ED, and that expression is 4x plus 6. We substitute in our value 5, and we end up with ED having a length, segment ED having a length of 26. Then we need to find the length DF, but DF is the same length as ED. Remember, we said that because D is halfway in between, so we have two congruent segments, and that means that DF is also equal to a length of 26. Last of all, we want to find the length EF, and we could do that a couple of different ways, but we know that ED plus DF is equal to EF. And if we're trying to find EF, we can just say it's 26 times 2, or 26 plus 26. So EF has a length of 52. That is it for lesson 1.2. So you are going to be working on the practice problems next. Remember that if you have any questions about anything in these notes, go ahead and make a notation in your note file, and let's talk about it when we're back in class together.